What if we nuked a hurricane? Picture this. A massive storm churns across the Atlantic Ocean. Its eye wider than a city, its wind screaming at speeds that could tear buildings from their foundations. Satellites track its every move as it barrels toward the coast where millions of people live, work, and sleep. Meteorologists update their forecasts hourly, each prediction more dire than the last. Evacuation orders are issued. Highways clog with refugees fleeing inland. And somewhere, in a room filled with maps and weather data, someone asks a question that seems almost too absurd to consider. What if we just nuked it? What if we dropped a nuclear bomb directly into the heart of that swirling monster and blew it apart before it could make landfall? It sounds like something from a science fiction movie, doesn't it? The kind of audacious, almost ridiculous solution that a desperate protagonist might propose when conventional options have failed. But here's the thing that might surprise you. This isn't just a thought experiment dreamed up by screenwriters. This is a real idea that has been seriously proposed, repeatedly discussed, and even considered at the highest levels of government. And the question of whether we could nuke a hurricane has fascinated scientists, frustrated meteorologists, and captured the public imagination for decades. The notion seems to carry a certain appealing logic, at least on the surface. Hurricanes are destructive. Nuclear weapons are powerful. Why not fight fire with fire, or in this case, fight wind with atomic fury? The United States alone has experienced devastating hurricanes that have killed thousands, displaced millions, and caused hundreds of billions of dollars in damage. Hurricane Katrina in 2005. Hurricane Harvey in 2017. Hurricane Maria that same year, which turned parts of Puerto Rico into a disaster zone where people went months without electricity. The human cost is staggering. The economic toll is almost incomprehensible. So when faced with such destructive natural phenomena, it's understandable that people would search for dramatic solutions. The impulse to hit back at nature, to assert control over forces that seem uncontrollable, is deeply human. But as we'll discover, the reality of what would happen if we actually detonated a nuclear weapon inside a hurricane is far more complex, far more dangerous, and far more bizarre than most people imagine. Before we dive deep into the science and the consequences, let me ask you something. Have you ever stood outside during a truly powerful storm? Not just rain, but the kind of weather event that makes you genuinely concerned for your safety? Think about that feeling for a moment. The way the wind doesn't just blow but seems to push you, to have weight and intention. The way the air itself feels different, charged with electricity and moisture. The sound of it, not a whistle but a roar, like the earth itself is angry. Now multiply that sensation by a factor of hundreds. Imagine winds not at 40 or 50 miles per hour, but at 180 miles per hour, strong enough to drive pieces of straw through tree trunks, to turn sand into a cutting tool, to make the rain fall not downward but sideways, horizontally, with enough force to strip paint from walls. That's a hurricane. That's what we're talking about fighting with a nuclear weapon. The idea of nuking hurricanes has a surprisingly long history. It didn't originate with politicians or military strategists, though they would later become involved. The concept actually emerged from the scientific community itself. Born in an era when nuclear weapons were still new, their power not fully understood, and the hubris of humanity seemed boundless. During the 1950s and early 1960s, in the aftermath of World War II and in the midst of the Cold War, there was a genuine belief among some scientists and engineers that nuclear weapons might be tools for more than just warfare. Project Plowshare, for instance, was a United States program that explored peaceful uses of nuclear explosions. They seriously considered using atomic bombs to excavate harbors, create canals, extract natural gas from underground deposits, and even to alter landscapes for construction projects. In that context, using a nuke to stop a hurricane didn't seem quite so outlandish. It seemed like problem solving. It seemed like progress. The idea gained traction in part because of a man named Jack Reed, a scientist working for Sandia National Laboratories in the 1950s. Reed wasn't some crackpot with a wild theory. He was a legitimate researcher who wrote about the concept in meteorological journals, proposing that nuclear weapons might be able to disrupt the heat engine that powers hurricanes. His papers were technical, filled with calculations and thermodynamic principles, and they were taken seriously enough to spark ongoing discussions within the scientific community. But Reed's ideas were theoretical, exploratory, not necessarily advocating for immediate implementation. The problem is that once an idea enters the public consciousness, once it gets simplified and stripped of its caveats and conditions, it takes on a life of its own. And the idea of nuking hurricanes definitely took on a life of its own. Fast forward to more recent times, and the question keeps resurfacing. Multiple news reports over the years have indicated that during presidential briefings about hurricanes, the question has been raised again. Why don't we just bomb them? Can't we nuke these storms before they hit us? Officials from the National Oceanic and Atmospheric Administration, known as NOAA, have addressed this question so many times that they actually created a dedicated section on their website explaining why it wouldn't work. Think about that for a moment. A major scientific agency had to create an official FAQ page to explain why we shouldn't nuke hurricanes because people, including people in positions of power, kept asking about it. This isn't ancient history or forgotten pseudoscience. This is a recurring idea that refuses to die, despite all evidence to the contrary, because it appeals to something fundamental in how many people think about problems. Big problem, big solution. Overwhelming threat, overwhelming response. So let's get into the science. Let's understand what we're actually dealing with when we talk about hurricanes and nuclear weapons, because only then can we truly grasp why this idea, however appealing it might sound, would be not just ineffective but catastrophically dangerous. First, we need to understand what a hurricane actually is. It's not just a big storm. It's one of nature's most complex and powerful engines, a self-sustaining heat transfer mechanism that operates on a scale that dwarfs human engineering. Hurricanes form over warm ocean waters, typically when sea surface temperatures reach at least 80 degrees Fahrenheit or about 26.5 degrees Celsius. The warm water heats the air above it, causing that air to rise rapidly. As the warm, moist air rises, it creates an area of lower pressure beneath it. More air rushes in to fill that low pressure area, and it too gets heated and rises. This creates a cycle, a feedback loop that becomes self-reinforcing under the right conditions. As the warm air rises and cools, the moisture in it condenses into clouds and rain, and this condensation process releases enormous amounts of latent heat. This heat release is absolutely crucial. It's the fuel that powers the entire system. The released heat warms the surrounding air even more, causing it to rise even faster, which creates even lower pressure at the surface, which draws in even more air, which releases even more heat. The cycle accelerates. The Earth's rotation causes this rising column of air to begin spinning due to something called the Coriolis effect. In the northern hemisphere, hurricanes spin counterclockwise. In the southern hemisphere, they spin clockwise. As more and more energy gets pumped into the system, the winds increase. The clouds tower higher into the atmosphere. The eye of the storm forms at the center, a strange zone of relative calm surrounded by the eye wall, where the most intense winds and rainfall occur. The entire structure can grow to be hundreds of miles across, and it can sustain itself for days or even weeks as long as it remains over warm water. Now here's what's truly staggering about hurricanes from an energy perspective. A typical mature hurricane releases energy at a rate of about 600 trillion watts. 600 trillion. That's more than 200 times the entire world's electrical generating capacity. Another way to think about it is that a hurricane releases the energy equivalent of a 10 megaton nuclear bomb every 20 minutes through the condensation of water vapor alone. Every 20 minutes. Not over its lifetime, but continuously, as long as it's active. We're talking about a phenomenon that makes even our most powerful weapons look like firecrackers by comparison. A large hurricane might release energy equivalent to exploding a 10-megaton nuclear bomb every 20 minutes for over a week straight. Try to visualize that level of power. It's almost incomprehensible. The entire storm system contains energy levels that humans cannot match, cannot replicate, and certainly cannot simply overpower with our current technology. So what about the other half of this equation? What about nuclear weapons? To understand why nuking a hurricane wouldn't work, we need to understand what nuclear weapons actually do. When a nuclear bomb detonates, it releases an enormous amount of energy in several forms. There's the blast wave, a sudden increase in air pressure that radiates outward from the explosion at supersonic speeds, capable of flattening buildings and killing anyone in its path. There's thermal radiation, intense heat that can ignite fires miles away from ground zero and cause severe burns to exposed skin even at great distances. There's ionizing radiation, the immediate burst of gamma rays and neutrons that can be lethal to living things. And for those bombs detonated near the ground or in the water, there's radioactive fallout, the debris and particles that have been irradiated and can spread contamination over vast areas. The size of nuclear weapons is measured in yield, typically described in kilotons or megatons of TNT equivalent. The bomb dropped on Hiroshima in 1945 had a yield of about 15 kilotons. Modern nuclear weapons in military arsenals range from less than 1 kiloton for tactical nukes up to multiple megatons for strategic weapons. The largest nuclear weapon ever detonated was the Soviet Tsar Bomba in 1961, which had a yield of 50 megatons. The fireball alone was 5 miles in diameter. The flash could be seen from 600 miles away. The mushroom cloud rose 40 miles into the atmosphere. Windows shattered hundreds of miles from the test site. It was the most powerful explosion ever created by humans. And yet, compared to the total energy in a hurricane, even the Tsar Bomba was relatively small. That 50 megaton explosion represented about the same amount of energy that a hurricane releases through condensation in less than 2 hours. Think about that. The largest bomb ever built, a weapon so powerful that it frightened even its creators, contained less energy than a hurricane naturally processes in the time it takes to watch a movie. But energy comparison isn't even the main problem with the nuke a hurricane idea. Even if we had a weapon powerful enough, which we don't, the way that energy is distributed matters enormously. A nuclear explosion releases its energy in a fraction of a second in a relatively small volume of space. A hurricane distributes its energy over hundreds of miles and sustains itself over days or weeks. It's not just about the total amount of energy. It's about how that energy is organized, distributed, and sustained. A nuclear explosion is a brief, localized disruption. A hurricane is a vast, self-sustaining system. Trying to disrupt a hurricane with a nuke is like trying to stop an ocean current by throwing a rock into the water. The scale mismatch is so enormous that the intervention becomes meaningless in the context of the larger system. Let's imagine, hypothetically, that someone decided to proceed with this plan anyway. Walk through what would actually happen step by step, and you'll see why this ranks among the worst ideas in the history of disaster management. The first proposal that's often suggested is to detonate a nuclear weapon in the eye of the hurricane, the calm center around which the storm rotates. The theory, such as it is, suggests that the explosion might disrupt the low-pressure center or create enough downward force to collapse the structure of the storm. So picture this. A bomber or a missile carries a nuclear warhead into the eye of a Category 5 hurricane. This alone is an almost impossibly dangerous mission. The eye is surrounded by the eye wall, where the most violent conditions exist. The turbulence would be severe enough to tear most aircraft apart. The winds in the eye wall can exceed 180 miles per hour with sudden, unpredictable changes in direction and intensity. But let's say, somehow, the weapon is delivered and detonated in the eye at optimal altitude. The fireball expands. The blast wave races outward. And then what? The hurricane is a low-pressure system maintained by continuous energy input from warm ocean water below. The nuclear explosion creates a brief moment of extremely high pressure and temperature, but this dissipates rapidly. The storm is hundreds of miles wide. The explosion affects a zone maybe a few miles in diameter significantly. Within seconds, the larger circulation of the hurricane would begin to fill in the disrupted area. The warm ocean below continues to pump energy into the system. The heat engine hasn't been turned off. Its power source, the warm water, hasn't been eliminated. At best, you might create a temporary disturbance in the eye. At worst, and far more likely, you accomplish absolutely nothing except adding one more element to the scenario. And this is where things go from ineffective to catastrophic. You've just detonated a nuclear weapon in the atmosphere, and all of that radioactive fallout, all of those lethal particles, are now being incorporated into the hurricane circulation. A hurricane is essentially a massive heat and moisture distribution system. It sucks up water from the ocean surface, carries it high into the atmosphere, and spreads it over hundreds or thousands of miles as rain. Now imagine that same system, but instead of just distributing water, it's distributing radioactive isotopes. Cesium-137, strontium-90, iodine-131, plutonium particles, and dozens of other deadly radionuclides, all suspended in the water vapor, all being carried along with the storm circulation. The hurricane, which was already a natural disaster, has now become a radioactive nightmare, a dirty bomb on a continental scale. As the storm moves, it would rain contaminated water across every area it passes over. Farmland would become poisoned. Water supplies would be irradiated. Entire regions could become uninhabitable for decades or longer depending on the isotopes involved and their half-lives. Consider the scale of rainfall from a hurricane. Hurricane Harvey in 2017 dropped more than 60 inches of rain in some parts of Texas. That's 5 feet of water. Now imagine if even a fraction of that water carried radioactive contamination. The cleanup would be impossible. You can't decontaminate an entire state. You can't filter radiation out of soil across thousands of square miles. The affected areas would simply be lost, written off, evacuated permanently. And the hurricane wouldn't care. It would keep moving, keep raining, keep spreading that contamination across its entire track. If it made landfall, and hurricanes generally do, you'd have radioactive rain falling on cities. If it stayed over the ocean, you'd be contaminating the marine environment on an unprecedented scale, poisoning fisheries, disrupting ecosystems, and potentially affecting ocean currents and food chains in ways we can't fully predict. But wait, you might think, what if we detonated the weapon early in the hurricane's life cycle, when it's still just a tropical depression or a tropical storm, before it has fully organized into a mature hurricane? Surely it would be easier to disrupt then. This idea has also been proposed, and it has its own set of problems. First, there's the prediction problem. Meteorologists track dozens of tropical disturbances during hurricane season, most of which never develop into hurricanes. They dissipate on their own or encounter conditions that prevent further strengthening. Wind shear, dry air intrusion, cooler water, all of these factors can kill a developing storm naturally. So you'd need to identify which storms will actually become dangerous hurricanes, and you'd need to do so early enough to act. Despite major advances in meteorology, this kind of prediction is still not perfectly reliable. You'd inevitably end up nuking storms that would have died on their own, wasting weapons and spreading radiation for no reason. Second, even a developing tropical storm is still a large weather system, and the same fundamental problem applies. You're trying to disrupt a heat engine powered by warm ocean water. Detonating a weapon in a tropical storm might temporarily disrupt its organization, but as long as the underlying conditions favor storm development, the warm water, the low wind shear, the moist atmosphere, the system will likely reorganize. You haven't changed the environmental conditions. You've just created a temporary disturbance. It's like trying to prevent a pot of water from boiling by stirring it vigorously for a few seconds while leaving it on the stove. The heat source is still there. the water will still boil. Meanwhile, you've added radioactive contamination to a storm system that covers thousands of square miles of ocean and atmosphere. There's another proposal sometimes suggested, and it's even more elaborate. What if we detonated multiple nuclear weapons around the hurricane, creating blast waves that converge on the center and collapse the structure? Setting aside the logistical nightmare of coordinating multiple nuclear detonations in precise timing around a moving storm system, this idea fails for the same fundamental reasons. The energy mismatch is still enormous. The hurricane's power source is still intact. And now, instead of contaminating the environment with one nuclear weapon, you're using several, multiplying the radioactive fallout and the environmental damage. You'd create a scenario where multiple plumes of radioactive material are being mixed into the hurricane circulation from different points, ensuring even more widespread contamination. It's a solution that takes a bad idea and makes it exponentially worse. Let's talk about the political and international implications, because this isn't just a scientific or environmental issue. The use of nuclear weapons is governed by international treaties and norms that have been carefully constructed over decades to prevent nuclear conflict and limit proliferation. The Limited Test Ban Treaty of 1963 prohibits nuclear weapons tests in the atmosphere, in outer space, and underwater. It was signed specifically because atmospheric testing was spreading radioactive fallout globally, causing measurable increases in background radiation and raising cancer rates. Using a nuclear weapon to attack a hurricane would violate this treaty. It would constitute an atmospheric nuclear detonation, and it wouldn't matter that the intent was supposedly peaceful or defensive. The radiation doesn't care about intentions. The fallout would spread regardless. Moreover, imagine the international response. The United States detonates a nuclear weapon in the Atlantic Ocean or the Caribbean to try to stop a hurricane. That radioactive fallout doesn't respect borders. It spreads with the wind and the ocean currents. Caribbean nations, Central American countries, potentially parts of South America, and even Europe, depending on atmospheric circulation, could all receive fallout from this action. They weren't consulted. They didn't consent. But they're bearing the consequences of another nation's decision to use nuclear weapons in the shared global environment. This would be seen as an act of aggression, or at minimum, an act of criminal negligence. The political fallout, if you'll pardon the pun, would be immense. International condemnation, potential sanctions, the erosion of treaties and norms that have kept nuclear weapons largely in use since 1945, all of this could result from an attempt to nuke a hurricane. There's also the domestic political dimension. Public opinion on using nuclear weapons for any purpose is complex and often divided. Even framing it as a defensive measure against natural disasters wouldn't necessarily create consensus. Many people would rightly be horrified at the idea of intentionally releasing radiation into the environment. Environmental groups would oppose it. Public health organizations would oppose it. Neighboring countries would oppose it. The political cost of even proposing such an action seriously, let alone implementing it, would be staggering. And if it didn't work, if the hurricane kept coming and now it was radioactive, the political leaders who authorized the action would face consequences that would make typical political scandals look trivial by comparison. You'd be responsible for both failing to stop the hurricane and for deliberately contaminating vast areas with radiation. It's a lose-lose scenario of almost unprecedented magnitude. Now let's examine some of the scientific studies that have actually been conducted on this question, because despite all the obvious problems, researchers have actually modeled what would happen if we nuked a hurricane. These studies aren't advocacy. They're not recommendations. They're scientific analyses done to definitively answer the question and, hopefully, put it to rest. One of the key findings from these studies involves the temperature change that a nuclear explosion would create in the hurricane. A nuclear weapon releases tremendous heat, yes, but that heat dissipates quickly, and the volume of air and water involved in a hurricane is so vast that the temperature change would be negligible. One study calculated that even a very large nuclear explosion would raise the temperature in the hurricane by less than 1 degree Celsius, and that's being generous with the assumptions. 1 degree in a storm system that's already dealing with temperature differentials and energy flows thousands of times larger. It would be completely insignificant. The hurricane wouldn't notice. Another finding relates to the blast wave and wind disruption. The blast wave from a nuclear explosion travels outward at supersonic speeds initially, but it weakens rapidly with distance. In the open atmosphere, especially in the chaotic environment of a hurricane where winds are already extreme, the blast wave dissipates quickly. Within a few miles of the detonation, the effect would become indistinguishable from the hurricane's own wind fluctuations. You're not creating enough sustained force to counteract the hurricane's circulation. You're creating a brief pulse that gets absorbed into the larger system. It's like clapping your hands once to try to stop a freight train. The energy you're inputting is real, but it's trivial compared to the momentum of what you're trying to stop. Some researchers have also explored whether you could use nuclear explosions to somehow heat the upper atmosphere above a hurricane, creating conditions that might disrupt its vertical structure. Hurricanes need a particular vertical temperature profile to maintain themselves. If you could dramatically alter that profile, in theory, you might weaken the storm. But the calculations show that heating the upper atmosphere over a hurricane would require sustained energy input at levels we simply cannot achieve. A single explosion wouldn't do it. Even multiple explosions wouldn't do it. You'd need continuous energy input over a large area for an extended period, and we don't have any technology that can do that, nuclear or otherwise. And again, even if we could, the radioactive contamination would make the cure far worse than the disease. What's fascinating, and perhaps telling, is that no serious meteorologist or atmospheric scientist advocates for nuking hurricanes. The people who actually study these storms for a living, who understand their physics and their power, uniformly reject the idea. The only context in which it comes up in scientific literature is when researchers are explaining why it wouldn't work. NOAA's official statement on the matter is unambiguous. They point out the energy mismatch, the ineffectiveness of the explosion, and the catastrophic problem of radioactive fallout. They note that the idea has been around for decades and has been thoroughly examined and discredited. The scientific consensus is clear and has been for a long time. And yet the idea persists in popular imagination and occasionally in political discussions. Why is that? Part of the answer lies in how people think about problems and solutions. There's a cognitive bias called the law of the instrument, sometimes summarized as, if all you have is a hammer, everything looks like a nail. Nuclear weapons are the most powerful tools humans have ever created for releasing energy quickly. When faced with something as powerful and destructive as a hurricane, it's almost instinctive for some people to reach for the most powerful tool available. It feels like matching scale with scale, power with power. The problem is that not all problems can be solved with raw power, and not all tools are appropriate for all tasks. A hurricane isn't a nail, and a nuclear weapon isn't the right hammer even if it were. The very nature of the problem, a self-sustaining atmospheric heat engine, means that brute force approaches are likely to fail. You need to address the underlying energy source, and that means the warm ocean water, which we have no way to cool over the vast areas necessary. There's also an element of hubris in the nuka hurricane idea, a belief that human technology should be able to control nature, that we should be able to impose our will on natural systems. This isn't a new impulse. Throughout history, humans have attempted to control weather and climate through various means. Cloud seeding to produce rain, fog dispersal for aviation safety, even larger-scale proposals like damming the Bering Strait or redirecting ocean currents. Some of these efforts have had limited, localized success. Most have failed or produced unintended consequences. The scale of Earth's climate and weather systems is so vast, and the interconnections are so complex, that our interventions often create as many problems as they solve. A hurricane is nature operating at a scale that dwarfs human engineering. Recognizing that isn't defeatism, it's realism. It's understanding our place in the natural world and the limits of our current technology. So if nuking hurricanes won't work, what does work? What can we actually do about these devastating storms? The answer, perhaps unsatisfying to those looking for dramatic solutions, lies in better prediction, better preparation, and better infrastructure. Meteorological science has made enormous strides in hurricane forecasting over the past few decades. Satellite technology allows us to spot tropical disturbances early and track them continuously. Weather balloons, aircraft reconnaissance, ocean buoys, and sophisticated computer models help us predict a hurricane's track, intensity, and impacts with increasing accuracy. The lead time for hurricane warnings has increased dramatically. We can now typically predict landfall location within about 100 miles several days in advance, giving people time to evacuate or prepare. Intensity forecasting is harder and less accurate, but it too has improved. This prediction capability saves lives. It gives vulnerable populations time to get out of harm's way. Preparation means having robust emergency management systems in place. Evacuation plans, emergency supplies, shelters, communication networks, all of these need to be established and tested before a hurricane strikes. It means public education so that people understand the risks and know how to respond. It means coordination between local, state, and federal agencies so that response is quick and effective. After Hurricane Katrina exposed massive failures in emergency management, there were significant efforts to improve these systems. The response to later hurricanes, while never perfect, has generally been better organized and more effective. Lives are saved not through dramatic technological interventions, but through careful planning and execution of evacuation and response procedures. Infrastructure is perhaps the most important long-term solution. Buildings designed and constructed to withstand hurricane-force winds suffer far less damage than those built to lower standards. Building codes in hurricane-prone areas have been strengthened over time, requiring features like reinforced roofs, impact-resistant windows, and stronger connections between structural elements. Elevating buildings in flood-prone areas reduces damage from storm surge. Preserving and restoring natural barriers like mangrove forests, dunes, and wetlands provide some protection against storm surge and wave action. These ecosystems act as buffers, absorbing energy from the storm before it reaches developed areas. Infrastructure also means hardening critical systems like power grids, water treatment plants, hospitals, and communication networks so they can survive storms and continue functioning, or at least recover quickly. These solutions aren't glamorous. They don't make for exciting headlines, but they work. They reduce deaths, injuries, and economic losses. They represent our actual best defense against hurricanes. There is ongoing research into whether hurricanes could potentially be weakened through other means. Some scientists have explored the idea of cooling ocean surface temperatures in the path of a developing storm, perhaps by pumping cooler water from the depths to the surface. The physics is sound in principle. Reduce the ocean temperature below the threshold needed for hurricane formation, and the storm loses its energy source. The practical problems, however, are immense. The area you'd need to cool is vast. A developing hurricane might be drawing energy from an ocean area hundreds of miles across. The amount of water you'd need to move, and the energy required to do so, is staggering. Current proposals involve arrays of pumps or wave-driven devices, but scaling these up to the necessary size would require resources and infrastructure that don't currently exist. It remains a theoretical possibility being researched, but not a near-term solution. Another idea involves dispersing chemical compounds on the ocean surface to reduce evaporation, again cutting off the hurricane's energy source. Evaporation of ocean water provides the moisture and latent heat that fuel the storm. Reduce evaporation, and you reduce energy input. The same scaling problems apply. You'd need to cover enormous ocean areas, and you'd need to do so in advance of the storm's arrival. The environmental impact of dispersing large quantities of chemicals in the ocean would also need to be carefully considered. There's potential for unintended ecological harm. And like the cooling idea, this remains in the realm of theoretical research rather than practical implementation. The key difference between these ideas and the NUKED hurricane concept is that these approaches at least target the actual energy source of the storm, the warm ocean water, rather than trying to directly fight the hurricane circulation with brute force. Perhaps one of the most important things to understand about hurricanes is that while they're destructive and dangerous, they're also a natural part of Earth's climate system. They serve functions in the global distribution of heat and energy. The tropics receive more solar energy than the polar regions. This creates a temperature imbalance that drives atmospheric and oceanic circulation. Hurricanes are part of how the Earth redistributes this heat, moving warmth from the tropics toward higher latitudes. They also bring rainfall to regions that depend on it. Some areas receive a significant portion of their annual precipitation from tropical cyclones. Eliminating hurricanes entirely, even if we could, would have unpredictable effects on global climate patterns. We might solve one problem while creating others. This doesn't mean we should be complacent about hurricane damage, but it does mean we need to think about living with hurricanes, managing the risks they pose, rather than fantasizing about eliminating them entirely. Climate change adds another layer of complexity to the hurricane question. As global temperatures rise, ocean temperatures are also increasing. Warmer oceans mean more energy available for hurricanes. There's ongoing scientific research and debate about exactly how climate change is affecting hurricane frequency and intensity. The consensus seems to be that we may not see more hurricanes overall, but we're likely to see a higher proportion of very intense hurricanes, Category 4 and 5 storms. We're also likely to see increased rainfall from hurricanes because a warmer atmosphere can hold more moisture. Storm surge may worsen due to sea level rise. In other words, the hurricane problem isn't getting easier. It's getting harder. This makes the temptation to look for dramatic solutions even stronger. When the threat is growing, people want solutions that match that growing threat in ambition and scale. But this is exactly when we need to be most careful about embracing bad ideas. Desperation can lead to poor decision-making. The worse the hurricane problem becomes, the more important it is that we focus on solutions that actually work rather than wasting resources on approaches that are scientifically unsound. Investing in better infrastructure, improving building codes, enhancing prediction and warning systems, developing sustainable coastal management practices, these are the solutions that will actually protect people. They're not as dramatic as nuclear explosions, but they're effective. Climate adaptation isn't exciting. It's often expensive and politically difficult. It requires long-term thinking and sustained commitment. But it's necessary, and it's achievable. Nuking hurricanes is neither necessary nor achievable. It's a distraction from real solutions. Let's consider the broader historical context of humans attempting to control weather. Cloud seeding, the practice of dispersing substances into clouds to encourage precipitation, has been used since the 1940s with mixed results. It can enhance rainfall from clouds under certain conditions, but it's not reliable and the effects are modest. During the Vietnam War, the United States conducted Operation Popeye, a cloud seeding program intended to extend the monsoon season over parts of the Ho Chi Minh Trail, hoping to disrupt enemy supply lines with mud and floods. The effectiveness is disputed, but it did lead to international concerns about weather modification as a weapon, eventually resulting in the Environmental Modification Convention of 1977, which prohibits hostile use of weather modification techniques. This treaty exists because people recognized that weaponizing weather could have catastrophic and uncontrollable consequences. There was also Project Storm Fury, a real scientific program conducted by the United States government from 1962 to 1983 that attempted to weaken hurricanes, though not with nuclear weapons. The approach involved seeding hurricanes with silver iodide to encourage supercooled water in the eye wall to freeze. The theory was that this would release latent heat outside the eye wall, causing a new eye wall to form at a larger radius. A larger eye wall would have lower wind speeds due to conservation of angular momentum, similar to how a figure skater slows down when extending their arms. The project conducted several seeding flights into hurricanes, and some storms did appear to weaken after seeding. However, scientists eventually concluded that they couldn't prove the seeding caused the weakening. Hurricanes naturally fluctuate in intensity, and natural eye wall replacement cycles occur even without human intervention. Additionally, they realized that many hurricanes don't have the right internal structure for the seeding to work. Project Storm Fury was eventually abandoned, not because it was dangerous like nuking would be, but because it didn't reliably achieve its goal. It's a useful lesson. Even a scientifically grounded approach to hurricane modification, one that didn't involve nuclear weapons or massive environmental risks, turned out to be impractical. The story of Project Storm Fury actually highlights something important about the NUKED hurricane idea. When serious scientists and engineers actually try to modify hurricanes, they think carefully about the storm's physics, they design interventions that target specific mechanisms, and they test carefully. They don't just throw raw power at the problem and hope it works. And even with careful scientific approaches, hurricane modification turned out to be far harder than anticipated. This makes the NUKED hurricane idea look even worse by comparison. It's not even a careful, targeted intervention. It's just brute force applied without regard for the physics involved. If a well-designed scientific program like Storm Fury couldn't reliably weaken hurricanes, what chance does a crude approach like nuclear detonation have? The answer is none. No chance at all. Think about the timeline of a hurricane and when intervention might even be possible. Hurricanes begin as tropical disturbances, areas of disturbed weather in the tropics that may or may not develop further. Most don't. Those that do organize into tropical depressions when they develop a closed circulation and sustained winds up to 38 miles per hour. Some tropical depressions strengthen into tropical storms with winds from 39 to 73 miles per hour. This is when they receive a name. Only some tropical storms further intensify into hurricanes with winds of 74 miles per hour or greater. Hurricanes are categorized on the Saffir-Simpson scale from Category 1, winds 74 to 95 miles per hour, up to Category 5, winds exceeding 157 miles per hour. The entire process from tropical disturbance to major hurricane can take days or even weeks, and it's heavily dependent on environmental conditions. At what point would you intervene? Too early, and you might be nuking weather systems that would never become dangerous. Too late, and you're facing a fully developed hurricane where the intervention is even less likely to work. There's also the operational challenge. Delivering a nuclear weapon to a specific location in a hurricane is extremely difficult. Missiles could potentially do it, but targeting a moving storm with precision would be challenging. Aircraft delivery would require flying into the hurricane, which is dangerous even for specially equipped reconnaissance aircraft. The turbulence, icing, lightning, and extreme wind shear make such missions hazardous. The Air Force Reserve hurricane hunters regularly fly into storms to gather data, and it's considered one of the most dangerous jobs in aviation despite extensive safety protocols and specially modified aircraft. Now imagine trying to do the same thing but with the added complexity of delivering and detonating a nuclear weapon at a precise location and altitude. The technical challenges are substantial even before you consider whether the detonation would accomplish anything useful, which it wouldn't. Let me pose another question for you to consider. If nuking hurricanes were a viable solution, why hasn't any nation with nuclear weapons actually tried it? It's not for lack of hurricanes. Tropical cyclones, the generic term for these storms called hurricanes in the Atlantic and Eastern Pacific, typhoons in the Western Pacific, and cyclones in the Indian Ocean, occur all over the world's tropical oceans. Countries with nuclear weapons include the United States, Russia, China, France, and the United Kingdom, all of which have territories or interests in tropical cyclone-prone regions. India and Pakistan, both nuclear-armed, face cyclones regularly in the Indian Ocean and the Bay of Bengal. If this were a viable strategy, wouldn't someone have attempted it by now, if only as an experiment? The fact that no nuclear nation has ever seriously attempted to bomb a hurricane, despite many having both the weapons and the motivation, should tell you something. The people with access to both the weapons and the scientific expertise to evaluate the idea have concluded it's not worth doing. The only place the idea has any traction is in popular imagination and occasional political discourse, contexts where scientific rigor sometimes takes a back seat to intuitive appeal. The psychological appeal of the NUKED hurricane idea is worth exploring because it reveals something about how humans think about problems, especially big, scary problems. Hurricanes are terrifying because they're powerful and, from an individual's perspective, uncontrollable. You can't fight a hurricane. You can't negotiate with it. You can only get out of its way or hunker down and hope your shelter holds. This feeling of powerlessness is deeply uncomfortable for people, especially in cultures that emphasize human agency and control. Nuclear weapons, meanwhile, represent the pinnacle of human power, the most destructive force we've ever harnessed. There's a certain emotional logic to the idea of fighting the ultimate natural threat with the ultimate human weapon. It feels symmetrical. It feels like taking control back from nature. But this emotional appeal is exactly why we need to be careful. Solutions that feel satisfying aren't necessarily solutions that work. In fact, the emotional satisfaction of a dramatic gesture can sometimes blind us to practical realities. This is related to a phenomenon psychologists call action bias. When faced with a problem, especially a crisis, people feel a strong urge to do something, even if doing nothing or taking subtle, less dramatic actions would actually be more effective. Sports fans see this in soccer goalkeepers during penalty kicks. Studies have shown that goalkeepers who stay in the center of the goal have a better chance of stopping the ball than those who dive to one side, but almost all goalkeepers dive. Staying put feels passive, like giving up, even though it's statistically the better choice. Diving, taking action, feels like fighting, like trying, even when it reduces your chance of success. The NUKED hurricane idea appeals to the same bias. Doing nothing, or rather, doing the boring work of infrastructure improvement and emergency preparedness, feels passive. It feels like we're just accepting the damage hurricanes cause. Bombing the hurricane feels active and aggressive. It feels like we're fighting back. But feelings aren't facts. The active approach, in this case, is actually worse than the supposedly passive approach. It's action bias run amok, potentially leading to catastrophic decisions. Another cognitive factor at play is the availability heuristic, the tendency to overestimate the likelihood or importance of things that come easily to mind. Nuclear weapons loom large in cultural consciousness. We've seen the images of mushroom clouds, the destroyed cities, the awesome, terrible power of atomic explosions. These images are vivid and memorable. They're available in our minds. So when we think about matching power, nuclear weapons come quickly to mind because we have such strong mental imagery associated with them. The energy in warm ocean water, the thermodynamics of latent heat release, the vast scale of atmospheric circulation, these things are harder to visualize. They're more abstract. So even though the hurricane's energy vastly exceeds a nuclear weapon's, the bomb feels more powerful because we have more visceral imagery of its effects. Our intuitions lead us astray because they're based on availability and vividness rather than on actual quantitative comparison. The question of why bad ideas persist despite being debunked is broader than just nuking hurricanes. We see it in many domains. Conspiracy theories, debunked medical myths, discredited historical claims. All of these have a way of surviving and even thriving despite contrary evidence. Part of the explanation is that not everyone has access to or trusts the scientific sources that debunk the ideas. Part of it is that correcting misinformation is harder than spreading it. A false claim can be simple and memorable. The correction often requires explaining complex concepts and presenting nuanced evidence. Part of it is motivated reasoning. If someone wants to believe something because it aligns with their worldview or gives them comfort, they'll find ways to discount contradicting evidence. And part of it is simply repetition. The more often an idea is mentioned, even in the context of debunking it, the more familiar it becomes, and familiarity can be mistaken for truth. The NUKED hurricane idea benefits from all of these factors. Keeps getting mentioned, it has intuitive appeal, and the explanation for why it's wrong requires understanding atmospheric physics and nuclear weapons effects in some detail. Education is the long-term solution to persistent bad ideas. Not just science education in the narrow sense of teaching facts, but science literacy in the broader sense of teaching how to think about evidence, how to evaluate sources, how to recognize when intuition might be misleading, and how to proportion belief to evidence. A scientifically literate population doesn't just know that nuking hurricanes is a bad idea. They understand why it's a bad idea, and they have the tools to evaluate similar claims critically when they encounter them in the future. This kind of education is challenging. It requires sustained effort, good curricula, trained teachers, and a cultural value placed on evidence-based reasoning. But it's achievable, and it's one of the best investments a society can make. Let's return to the concrete question of hurricane damage and what actually reduces it. Data from recent decades shows clearly that improved building codes save lives and reduce property damage. After Hurricane Andrew devastated South Florida in 1992, revealing widespread poor construction and code enforcement problems, Florida substantially strengthened its building codes. Subsequent hurricanes hitting areas built to the newer codes have caused far less structural damage than Andrew did. This doesn't make for exciting news coverage. It's hard to film a story about buildings that didn't collapse, but the evidence is clear. Engineering solutions work. Similarly, evacuation procedures, when followed, dramatically reduce deaths. The majority of hurricane fatalities occur when people don't evacuate flood-prone areas before storm surge arrives, or when they venture out during the storm. Improving compliance with evacuation orders, making evacuation more accessible to people without cars or resources, and providing adequate shelter for evacuees all contribute to reducing deaths. Early warning systems are another proven solution. The difference in death tolls between countries with advanced meteorological capabilities and those without is stark. When Cyclone Nargis hit Myanmar in 2008, it killed at least 138,000 people, with many estimates considerably higher. The country's meteorological and emergency management systems were inadequate. Warnings didn't reach many vulnerable communities, and evacuation infrastructure was lacking. By contrast, when Hurricane Irma, a similar intensity storm, threatened the United States in 2017, millions of people evacuated from Florida and other areas. While Irma still caused over 100 deaths and tens of billions in damage, the death toll would have been orders of magnitude higher without the advanced warning and evacuation. The technology and systems that enable this, satellites, computer models, communication networks, trained meteorologists, emergency managers, they're not glamorous. They don't involve explosions or dramatic interventions, but they save thousands of lives every year. That's what an actual solution looks like. Economic development also plays a role, though it's complex. Wealthier communities can typically afford better construction, better infrastructure, and better emergency preparedness. They can afford to enforce building codes, maintain emergency equipment, and conduct regular drills and training. They can afford to rebuild quickly after storms. This is why hurricanes often cause more deaths in poorer countries, even when the storms are less intense. Poverty and inadequate infrastructure turn hurricanes into major humanitarian disasters. Economic development and disaster preparedness are linked. This doesn't mean poor communities are helpless. International aid, smart local planning, and community-based preparedness can all reduce vulnerability. But it does mean that addressing hurricane risk is tied to broader questions of development, inequality, and resource distribution. These are hard problems without quick fixes, but they're the real problems. Nuking hurricanes would do nothing to address any of this. It would, in fact, make things worse by adding radioactive contamination to areas already struggling with disaster recovery. What about the future? Are there any technologies on the horizon that might actually give us more control over hurricanes? It's worth being cautious about predictions. but we can identify some areas of potential progress. Climate modeling is continually improving, which may allow better long-term prediction of hurricane seasons and more accurate forecasts of individual storms. This would provide more lead time for preparation. Material science is developing stronger, lighter building materials that could make hurricane-resistant construction more affordable and practical. Advances in renewable energy and distributed power generation might make electrical grids more resilient to storm damage. Better batteries and backup power systems could keep critical facilities running even when the main grid fails. These aren't science fiction technologies. They're incremental improvements in existing fields that could collectively make us more resilient to hurricanes. Some researchers are exploring whether artificial intelligence and machine learning could improve hurricane forecasting by identifying patterns in vast datasets that humans might miss. Early results are promising, though it's still an area of active research. If AI systems could predict hurricane intensification more accurately, particularly rapid intensification events that currently challenge forecasters, it would improve warning times and evacuation decisions. There's also ongoing work in understanding the detailed physics of hurricane formation and intensification. The better we understand these processes, the better we can predict them and potentially identify any leverage points where intervention might be feasible. To date, no such leverage points have been identified that would allow safe, effective weakening of hurricanes, but research continues. The key difference between this research and the NUKED hurricane idea is that serious research is cautious, evidence-based, and aware of limitations. It doesn't promise miracle solutions. It works incrementally toward better understanding and marginally better capabilities. There's a philosophical dimension to all of this that's worth considering. The desire to control nature, to make the natural world conform to human needs and preferences, is ancient. Agriculture is a form of controlling nature, shaping ecosystems to produce food. Architecture is controlling space and shelter. Medicine is controlling biology to promote health. Much of human progress consists of exerting control over natural processes that would otherwise harm us or limit us. So the impulse to control hurricanes fits into a long tradition. But there's also a tradition of recognizing limits, of understanding that some natural forces are beyond our control and that the wise response is adaptation rather than domination. Different cultures and philosophies have drawn this line in different places. The question of whether we should try to control hurricanes, even if we could, is as much philosophical as technical. It touches on how we see ourselves in relation to nature and what kinds of risks we're willing to accept. Indigenous and traditional knowledge systems often emphasize living with natural cycles rather than trying to dominate them. Communities in cyclone-prone regions have developed sophisticated understandings of storm behavior, seasonal patterns, and appropriate responses built up over generations. This knowledge is increasingly recognized as valuable alongside scientific meteorology. Traditional building techniques in some regions, like elevated structures or flexible materials that bend rather than break in high winds, represent time-tested solutions to hurricane risk. The modern tendency to seek technological fixes sometimes overlooks the wisdom in these traditional approaches. A more balanced strategy would combine the best of scientific forecasting and engineering with traditional knowledge and community-based resilience. This integrated approach is more likely to be sustainable and culturally appropriate than top-down technological interventions, especially ones as extreme as nuclear weapons. The NUKED hurricane idea can also be seen as a symptom of a particular modern anxiety about loss of control. As climate change makes extreme weather more common and more severe, and as our complex technological society becomes more vulnerable to disruptions, there's a growing fear that we're losing our grip on the systems that keep us safe. This fear is not entirely irrational. We are facing serious challenges. But fear-driven decision-making often leads to bad outcomes. The solution to climate change and extreme weather isn't to lash out with desperate, ill-conceived geoengineering schemes. It's to do the hard work of reducing emissions, adapting infrastructure, improving social resilience, and accepting that some degree of uncertainty and risk is inherent in existence. That's not a satisfying message in the way that nuking hurricanes feels satisfying. It doesn't promise a quick fix or total control. But it's realistic, and it's achievable. Reality doesn't care about what feels satisfying. It cares about what actually works. Let me share some specific stories of hurricane impacts to make this more concrete. Hurricane Maria hit Puerto Rico in September 2017 as a high-end Category 4 storm. The wind damage was severe, but the long-term catastrophe was the infrastructure collapse. The electrical grid, already aging and poorly maintained, was completely destroyed. Most of Puerto Rico was without power for months. Some remote areas went nearly a year without electricity. Hospitals struggled to care for patients. Water treatment plants couldn't function. People dependent on medical equipment powered by electricity faced life-threatening situations. The official death toll was initially reported as 64, but later studies estimated nearly 3,000 excess deaths attributable to the hurricane and its aftermath, mostly from the prolonged infrastructure failure. Think about that. The vast majority of deaths weren't from the storm itself, but from the cascading failures that followed. No amount of nuclear explosions could have prevented that. What would have prevented it was a more resilient electrical grid, better emergency power systems, more robust infrastructure, better emergency response, adequate supplies and distribution networks. These are the real solutions. These are what actually save lives. Hurricane Harvey hit Texas in August 2017 and stalled over the Houston area, dumping unprecedented rainfall. Some locations received more than 60 inches of rain in a few days. The flooding was catastrophic. Homes, businesses, roads, all underwater. More than 30,000 people were displaced into temporary shelters. The economic damage exceeded $125 billion. Harvey's impact illustrates a particular challenge with hurricanes: the inland flooding from rainfall, which is becoming more severe as climate change allows the atmosphere to hold more moisture. Coastal storm surge gets a lot of attention, and rightly so, but inland flooding from hurricane rainfall can be equally devastating and affects a much larger area. Addressing this requires improved flood management, better land use planning to avoid building in flood-prone areas, upgraded drainage systems, and preserved natural areas that can absorb water. It requires accurate forecasting of rainfall amounts and flood potential. Again, none of this would be helped by nuclear weapons. All of it requires careful planning, investment in infrastructure, and smart policy. Hurricane Katrina in August 2005 remains one of the most traumatic disasters in recent American history. The storm itself was powerful, but the catastrophe was largely human-made. The levee system protecting New Orleans failed in multiple places, flooding much of the city. The failure was due to poor design, inadequate construction, and deferred maintenance. The evacuation and emergency response were chaotic and inadequate. People were trapped in the flooded city for days without adequate food, water, or medical care. The images of people stranded on rooftops, of the Superdome filled with desperate evacuees, of bodies floating in floodwaters, shocked the nation. Katrina killed over 1,800 people and caused an estimated $161 billion in damage. The lessons from Katrina are almost entirely about preparedness, infrastructure, emergency management, and social equity. The people who suffered most were those with the least resources, who couldn't evacuate, who lived in the most vulnerable housing, who were failed by inadequate government response. These are social and political failures, not failures of raw technological capability. You can't bomb your way out of institutional failure and inequality. These stories matter because they ground the discussion in reality. Hurricanes are not abstract problems to be solved with abstract weapons. They're events that affect real people, real communities, real lives. The solutions have to be grounded in understanding those real impacts and addressing the actual mechanisms of harm. The mechanisms are wind damage, which building codes and construction practices can mitigate. Flooding from storm surge, which coastal management and evacuation can address. flooding from rainfall, which drainage systems and land use planning can mitigate, infrastructure failure, which resilient design and redundant systems can prevent, social vulnerability, which economic development and equitable policy can reduce. None of these mechanisms would be addressed by detonating a nuclear weapon in the storm. Not one. The nuclear option doesn't engage with the actual problem at any level. It's a fantasy solution to a real problem, and indulging fantasies distracts from real solutions. Consider also the global perspective. The United States is not the only country affected by tropical cyclones. Bangladesh faces deadly cyclones regularly, with a history of catastrophic death tolls. In 1970, the Bola cyclone killed an estimated 300,000 to 500,000 people. In 1991, another cyclone killed over 100,000. Since then, Bangladesh has invested heavily in cyclone shelters, early warning systems, and disaster preparedness. The death toll from recent cyclones has been dramatically lower, sometimes in the hundreds rather than hundreds of thousands, despite the storms being just as powerful. This is concrete proof that preparedness saves lives on a massive scale. The Philippines faces numerous typhoons every year, some of exceptional intensity. Typhoon Haiyan in 2013 was one of the most powerful tropical cyclones ever recorded at landfall, with sustained winds possibly exceeding 190 miles per hour. It killed over 6,000 people and affected millions. Recovery was slow and difficult, complicated by poverty and weak infrastructure. These global examples show that hurricane and typhoon risk is a worldwide problem affecting hundreds of millions of people, and the solutions that work are universal. Better warnings, better shelters, better infrastructure, better preparedness. These work regardless of culture or location. Would any of these countries consider nuking a typhoon or cyclone if they had nuclear weapons? It's an interesting thought experiment. The answer is almost certainly no, because the scientists and emergency managers in these countries, just like those in the United States, understand that it wouldn't work and would create catastrophic contamination. The fact that this idea has primarily surfaced in American political discourse rather than scientific or international forums is telling. It reflects a particular cultural moment and a particular style of problem-solving rhetoric, rather than any serious strategic or scientific proposal. Other nuclear-armed nations that face tropical cyclones, notably China, India, and Pakistan, have not proposed nuking storms. They've invested in forecasting, infrastructure, and preparedness. The international consensus among people who actually deal with these storms is clear. Let's talk about radiation and fallout in more detail, because this is such a critical problem with the nuka hurricane idea that it deserves thorough examination. When a nuclear weapon detonates, it creates dozens of radioactive isotopes through the fission process and through neutron activation of surrounding materials. Different isotopes have different half-lives, the time it takes for half of the radioactive material to decay. Some, like iodine-131, have relatively short half-lives, about 8 days. Others, like cesium-137 and strontium-90, have half-lives around 30 years. Plutonium-239 has a half-life of 24,000 years. These materials emit radiation that can damage living tissue, causing acute radiation sickness at high doses and increasing cancer risk at lower doses. When a nuclear weapon is detonated in the atmosphere, these radioactive materials initially form a fireball and mushroom cloud that rises high into the atmosphere. Some of the larger particles fall back to Earth relatively quickly as local fallout, typically within hours or days, depositing high levels of radiation in the area downwind of the blast. Finer particles can remain suspended in the atmosphere for weeks, months, or even years, spreading globally as worldwide fallout. During the era of atmospheric nuclear testing in the 1950s and early 60s, before the Limited Test Ban Treaty, hundreds of nuclear weapons were detonated in the atmosphere. The fallout from these tests spread worldwide, causing measurable increases in background radiation levels globally and in concentrations of specific isotopes like strontium-90 in environments and organisms everywhere on Earth. This contamination contributed to increases in cancer rates, particularly in areas downwind of test sites. It's why the treaty was signed, to stop this global contamination.